Welcome, everybody, and welcome to those joining with us online. I'd like to start by respectfully acknowledging the Wurundjeri people of the Kulin Nation, who are the traditional owners of the lands on Swinburne's Australian campuses are located in Melbourne's east and outer east, and pay my respects to their elders past, present, and emerging. National Science Week is Australia's annual celebration of science and technology. Running each year, it features more than 1,000 events across Australia, including those delivered by universities, schools, research institutions, libraries, museums, and science centres. I'd like to thank you for joining us this evening. Tonight, we will hear from Professor Alan Duffy, who is a professional astrophysicist creating universes, or perhaps I should say multiverses, on Swinburne's supercomputers. With this computational might, Alan seeks to understand how galaxies are born and how they grow. Technically, I think this makes Alan a guardian of the galaxy. Alan also hunts for the telltale signs of dark matter right here in Victoria. That's Nobel Prize-winning stuff, Alan, and we all hope you prove worthy. I think my jokes are bordering along the dad line now. So without further ado, let's hear about a topic that we'll all enjoy, the science of superheroes from screen to laboratory. Take it away, Alan.
Thank you, Brenton, for that. Nice and embarrassing. Well, thank you all for coming this evening and also for joining online. Yes, so I'll be talking about the science of science fiction films, of superhero films, of just films in general, both the best and, I have to be honest, the absolute worst films. So bear yourselves, it's going to get difficult. And I'm doing that because more people will see science through Hollywood than the classroom. So that exposure to science in Hollywood matters, if that's where the primary source of information for people is around how science works. And as I'll show tonight, if you're scientifically accurate, it doesn't mean that your movie is somehow boring. In fact, the best movies have the best science, as we'll discover this evening. Now, I have an immense debt of gratitude to Brenton, Dr. Brenton Hall, for his work in this presentation. And I also have a huge debt of gratitude to Swinburne Library, because I don't know if any of you are aware, but there is such a thing as copyright in Australia, and it's very onerous. And the library helped me figure out which of the movies we could show you tonight without Brenton having to go to jail, since it's his name up there and not mine. So my thanks to the library. What they've discovered, in fact, is there's nothing I can show you actually that doesn't break copyright. So what I've done entirely legally is embed YouTube trailers. Legal, that's why you keep seeing YouTube pop up. For those scenes that don't demonstrate the science, well, you'll see how I managed to get around that. Okay. So let's begin. We are all familiar, I hope, with this rating system, how we evaluate films based on their appropriateness for age, about their content. So it makes complete sense from my point of view to have a similar rating system for the science of films. We have G, which I think fairly explanatory, is good physics. Everyone's okay with that. With PG, that will be pretty good physics. That's, maybe mostly, there's one or two little things, but we can forgive it. That's fine. Now, M, just modest physics. Now it's getting a little touchy. Yeah, we're not so sure about some of the scenes, but by and large, at least they've tried. And then, of course, it begins to get quite serious. We have MA, where it begins to just be completely not suitable. And then, of course, the absolute warning is restricted for R, which is restricted to non-scientists only. So as a scientist, you watch this film, you're going to have just incredible rage and anger about how bad it all is. And it'll be very bad for your health and sanity. So this, thankfully, is a bracket rarely applied as a category. Now, one of the key concepts that we discover and talk about at Physics 101 here at Swinburne, and indeed as an astronomer, is the concept of weightlessness. And we see that done well, we see it done badly, but one of the best is a film called Gravity. And we'll watch it twice. So just enjoy it the first time around. And again, YouTube. Okay, so we've enjoyed it. I want us to watch it a second time. And this time, we're going to try to enjoy the science as much as the wonderful graphics and soundtrack. So weightlessness is not the same as having, in any way, not experiencing gravity. The key is objects around the Earth are falling under gravity. Gravity is still up there in space. That's why the space station, that's why the shuttle, that's why the Hubble Space Telescope and George Clooney are all sitting around the Earth because gravity's holding on. But they're clearly moving in a strange and unaccustomed way to us on the ground, and that's because they're falling. So if you were to jump off a high board at a diving pool, you'll move your arms around. You don't actually you can't move around in any meaningful distance. Right? You can wave your arms, but that's not changing really much of the direction. You can do things about spinning your body around, as divers show, but fundamentally you're falling and you can't change that. And exactly the same way, the astronauts, they'll move around, wave their arms, but unless they propel, like George Clooney does, in a little bursts of propulsion in his backpack, or you are tied to something and you can exert a force on it, you're kind of stuck. You're just floating around. So watch that, and also watch for the debris, okay? Everyone's now going to watch the second time. Oh, she's in trouble. Okay, so this concept of weightlessness, it's chaotic, it's you're unable to control your motion unless you are able to literally hold on or push against some object or have thrusters yourself, right? Very difficult. This is why astronauts train for years. This is done almost perfectly in the film Gravity. The reason it's a G and not a PG is actually about the space junk. And at least from my point of view, space junk is a real hazard. There are hundreds of thousands of pieces of debris, size of coffee cup sizes, or tens of thousands, at least that size, and millions the size of little paint flecks, all of which would be hazardous to astronauts up there. They're traveling at tens of thousands of kilometers per hour. So space junk is a real problem, and it's getting worse. And satellites, when they get smashed by space junk, in turn make more space junk, and that hits more, and there's an avalanche effect, and eventually you get a whole orbit filled with space junk. It's a terrible thing, and Gravity does a great job of showing what is known as the Kessler Syndrome. This is the runaway avalanche of space junk, as predicted by Kessler, a NASA scientist. Now, the one thing that I think they get wrong in this, and for obvious reason, is if something is moving at 7 kilometers a second, will you see it? It's going to zoom by, and it has traveled 7 kilometers in that time. So I would suspect no. Now you kind of got shared orbits. Yeah, I get it. But I think in the main, that's the one thing that I would disagree with this. And there's actually some other stuff later on. But anyways, in other words, what a great way to start the science of sci-fi. One of the greatest films, perfect, near perfect science, and all the better for it. A place where it's not done so well, at least. Another example where it's done really well, is Apollo 13, where there are scenes where Tom Hanks is literally floating. And that's not CGI. They are literally floating because they're falling. In this, a plane known as the Vomit Comet, and the famous, very much sadly missed, Stephen Hawking, was floating around inside that. It goes up and then falls and plunges down. So you free fall, so just like the astronauts, but you're sheltered within the plane, so you don't feel the air rushing by you. So you just get to have those cool, iconic moments. So every scene, they had about 15, 20 seconds of weightlessness. So they were shooting these really tightly. I think one or two, they managed to get a couple of minutes. So very, very intense filming, but that's why it looks so good, so accurate, because it really is freefall. A show that doesn't do it quite so well is the use of what is just termed artificial gravity, right? So you're in space, you're now very far away from a planet, there's no gravity, and yet, oh, look, everyone looks like they're moving normally. One of my favorites. Okay, so Star Trek, love it as a series. Got to be honest with you, not the best physics. So in this, on the bridge of the Enterprise, everyone is standing like this. It's almost as if they're in a film studio lot and they don't have the budget to do anything different. So in Star Trek, they have some throwaway line that the Enterprise is generating its own gravity, artificial gravity somehow, and that's how they can all move around. Because the Enterprise itself, the ship is tiny, it's never going to generate enough gravity to have 1G what we experience on Earth. Now, does it matter? Well, I mean, not massively. It's pretty awful. It's actually some of the worst science you can ever get is in Star Trek. And yet, for a number of us, Star Trek did begin our love of science and space travel. So, you know, maybe it's not, maybe you don't always have to be that accurate, but it's fair to say that more, I think, good ideas in science, and certainly in space science, have been driven by another film that did it very well indeed. Does anyone know what? I'm always curious if everyone knows what film I would say, which is basically the best. Yeah. Spooky. All right. So much to love about that scene. There's just those few scenes. So in 2001, we have a vision of what space travel could look like. It involves very slow movement, very slow scenes, and that's because space is massive. Yes, things are moving at 7 to 10 kilometers a second, but space is big. So that's tick. Journeys to Mars will take NASA astronauts something like 9 months, as expected as part of Project Artemis. So everything in space takes a while. We see the use of AI, we see that go wrong. So that's tick, tick, or again, that's very much an accurate portrayal. I think perhaps the most important piece from, as a scientist myself, was the rotating space station. Did everyone see that? The slowly rotating wheel. Now can you tell what I did when I couldn't get the license for the exact scenes I needed? There is just a brief glimpse of the astronaut running in the corridor. And what they're doing is they're running on the inside of a spinning space station. And the reason they do that is something called centripetal acceleration. So if you've experienced this, if you've been on a roundabout, you know, at a playground or an amusement park, and you can feel the force, right? If you hold on, it's spinning around. You can feel yourself being thrown off the Ferris wheel or the merry-go-round. Sorry. So if you imagine that force flinging you out from the center is what the astronauts experience on that spinning space station, then it's going to feel like there's a force that's driving out through their feet. Now, in the scene, we've just, the astronaut is visibly running around the space station, but if we zoom out from the space station, what does it look like? They're just running, well, essentially standing still, running, but as the space station turns beneath their feet. Is another way to look at it, different frame of reference. We talk in physics about reference frames a lot and how sometimes it's easier to do the calculation in one or the other. Now, this is perfect physics. This is actually now how NASA will try to do artificial gravity, or any other, space company will try to do artificial gravity. Because it's rotating around, Remember I said about the merry-go-round, you feel like you're getting flung out away from the center? Well, the astronaut is getting flung out away from the center, which is at the top. So they're getting flung out that way, which feels a lot like a force of gravity pulling them into the floor. So in other words, as that space station wheels around, they're going to feel a force into the floor that is exactly what I'm feeling right now as gravity. And you can work out exactly how fast this needs to turn to give you the exact force of gravity as we experience on Earth. So here is one of Brenton's drawings. So here we have the astronaut on the inside of the space station. It's wheeling around. You're feeling a force pushing you into the ground. You, in response, you're sort of feel what's called a normal reaction force. You feel getting pushed back up. That's why the little end is, arrow is drawn in that way. The centripetal acceleration, the acceleration of that, essentially the force that you feel, if you want it to be exactly that of 1g gravity here on the surface of the Earth, there's an equation for that. And it's v squared. By the way, sorry, there's going to be equations tonight. Not many, but there are some. The equation is that the acceleration is equal to v squared, the speed of the rotation, divided by the radius. Now, you can rearrange that. How fast does that wheel have to rotate around? V is equal to the square root of r times that g, that acceleration. The radius here, we can assume, is about 200 meters, give or take. You're sort of eyeballing that picture. The gravity of Earth, 1g, is 9.8 meters per second squared. Oh, never noticed that before. So we then have the plug in the numbers and we can figure out the velocity, and it ends up being 44 meters per second. That's very fast, but it's a very big wheel. So how fast is the wheel going around? Any one point, the velocity has to be 44 meters a second. Well, we can rearrange that. It's omega equals v divided by r, doesn't matter. But in other words, we can figure out how fast is the rotation around. And for a very big wheel, it's 0.2 rads per second, or in real numbers, as Alex put it, 2 revolutions per minute. So just 2 revolutions per minute, incredibly elegant, slowly wheeling, just like the film showed you, is enough to generate a force pushing you in to the wall, which is the floor of your space shuttle as you, or of your craft, as you jog around the inside, exactly that of Earth's gravity. This is why I love this film. This actually inspires NASA astronauts today and engineers, and indeed engineers around the world to do this design. And there are, so there are a couple of who I spoke to very recently, in fact, very rich people who are doing this exact thing. It's crazy. It's going to happen really, really soon. All right, now, another common concept in physics is that of forces. So it's time to bring out the Avengers. Okay, so the Avengers. I do love the Marvel Cinematic Universe. I can't get rid of this bar, so my apologies if that's kind of annoying to people. There is an iconic scene, which I couldn't, yeah, it's fine. I'm sure, I don't think it will be too annoying. Where Hulk jumps up to a building. And if I'm honest, I was running out of time, so this is why this is this animation. So Hulk does a bend and leaps up to a building. He leaps. I found this building on Google Maps. All right, it's in New York, it's near the train station. I found it. And I could count how many floors he jumped up in that scene. And he just reaches it and just slams his hand into the concrete to hold himself in position. There's a kind of moment with Captain America, it's like Hulk smash, and it's really great. So he does this jump, and I thought, wow, that's fantastic. I have real data. As a scientist, I must investigate. So Knowing how high Hulk has jumped, 18 stories is about 60 meters. I can begin to investigate the physics of the scene. So, an equation we like to use, familiar perhaps to final year students at high school, certainly in your Physics 101 class, is this formula: v squared equals u squared plus 2as. V is the final velocity of Hulk. U is his initial. A is the acceleration. In this case, he's fighting against that of gravity. And S is the distance that he's jumped, 60 meters. Because Hulk just manages to reach 60 meters and stops and grabs the concrete, V, the final velocity, is 0. His initial velocity, then, we can rearrange the equation, and we get that it's square root of 2 times the acceleration he's fighting, which is the force of gravity he's fighting against, and the height he jumps. If gravity was stronger, say 4 times stronger, you'd have to jump twice as fast to get that height, right? So if I jump faster, I can go higher, right? That's just the basis of this formula. So I know how high he's jumped. I know the acceleration he has to jump against that of gravity is pulling him back. So we can work out that his initial speed that he left the ground was 34 meters per second. So what you say? Well, fascinatingly, you can then work out the force that Hulk must have to undertake such a jump. In the previous scene in 2001, we were talking about force equals mass times acceleration. And we'll reuse that formula. A more generalized form is that the change of momentum divided by the time it took you to do that change. So in other words, if I want to change the direction of something moving, I have to push it, right? There's a force. And if I have to change a lot of its momentum very quickly, then that takes an enormous amount of force. And in this instance, we can figure out that it's his mass times that initial velocity pushing up, and it must all happen in a certain amount of time. Now, here's the problem. In the scene, you can see he bends his legs and off he jumps. Now, the time it's taking him to do the jump, I did have to eyeball this. This isn't the most precise measurement. It looked like I really have too much time. My boss is in the room and she must be wondering why I've had so much time to do all of this. There is 3 frames-ish, right, in that scene. I think it was about 3 frames. And because it's about 30 frames per second-ish, I don't know, roughly speaking, that's about the animation sort of frame rate, at least on YouTube. So it looks like the jump takes about 0.1 second, right, to push against all that time in 1/10 of a second. You can go and check these numbers. The point is that the force Hulk applies with his legs to bend and push against the ground to do this huge jump to just about reach 60 meters is 86 kilonewtons. This is 3 Teslas at full acceleration, right? That's a pretty good force for the big man. Now, who just said that? Did the ground break? Yes, that's what I'm getting to. Yes, good. All right. I love how it's inspiring people already. So the pressure is relevant, not the force per se, but the force applied on what area. If you've ever had your foot stamped on by someone in heels, you're aware of that difference between force, which is their weight, versus the pressure, which is that force applied over a tiny little area that just puts the heel through the high heel through your foot. So in this instance, it's the force divided by the area. Now, I don't know the area of Hulk's feet. Surprisingly difficult to find a number. So in this instance, and so I should have said the mass of Hulk I've assumed is, there's a scene beside Captain America, he looks like 3 times bigger or something, give or take. Anyways, about 250 kgs, that's what I assume. I then had to assume his foot size. Again, I have too much time on my hands. I think the average human foot size is about 100 square centimeters. He's a big lad. Let's go 300 square centimeters, or 0.3 square meters, right? Plug in all of these numbers into the formula. The pressure of Hulk applied on the concrete works out to be 285,000, that's what the K means, 1,000 pascals. Now that seems like a lot, but it's actually not that much, or at least not that much for concrete. Concrete can take megapascal, millions of pascals. In other words, shockingly, that scene is good physics. I swear it's the only one in the whole of the Avengers. But to my surprise, the ability of Hulk to jump from the concrete and reach that 60-meter height, he would not crack the concrete, which is exactly what you asked. That was not a plant either. That was amazing. So that bit of the physics is good. Obviously, the fact there's a green guy that big powered by gamma rays doing a jump like that, that's not great physics, but at least the concrete bit is fine. Okay. What if Hulk wore heels? Okay, great. So let's do this in real time. Thanks for the on the spot. So if that number was a factor 10 times more, then it would be getting close. If it was 100 times more, then he would definitely puncture the little heel through the concrete. So that would be 0.3 square meters. So if instead of being 0.003, yeah, so about a heel. Actually, yeah, really close to an actual heel. Yeah, so at that point, if you could get Hulk in size 50 heels, the back of the high heel would absolutely go through the concrete. Thank you, yes. What? Oh, have I made a mistake? Oh my God. Okay, for everyone online, I've just been corrected. Hulk's foot size is 186. Oh, size 86. Okay, thank you. So there's an official foot size for the Hulk. Okay, well, I've learned something. All right, good. I could have been even more accurate like this fake scene. Now, that's awesome. So that was surprising, but turns out concrete is a good structure to build things from. Very high tensile pressure strengths. Another common concept we describe in science and physics is that of kinematics. It is the science of the mathematics of motion. So what better way to explore that than in one of the iconic films of my childhood, at least, that of Speed. So yes, it will blow. And then there's a scene where they do this. Yay, they jump the bridge. Okay, so there is this really iconic moment. The bus can't drop below a certain speed, otherwise the bomb goes off. And Keanu is there to save the day, but he's not yet the Matrix or John Wick, so he's not able to do anything other than just keep the thing driving straight, albeit Sandra Bullock does that, by the way, FYI, superhero. So she's in 2 of our films tonight, which is just a weird coincidence. Now, the bus is driving, meets a, because it can't stop, has to keep going. There is an unfinished bit of the freeway, and then it does that jump, as described. It literally goes straight across, yay, and it makes it. Now, even as a kid, I was like, that looks a bit weird. Does anyone know what the motion would be if you go straight? Do you do that? I'm seeing lots of hands do that. Yes, that's right. This is a terrible bit of physics. In actual fact, this is what would happen. There we go. So we all intuitively understand the physics of this scenario where your object will fall under the influence of gravity as a curve. Funny story, if you make that speed of the bus not 50 miles an hour, but something like 50,000 miles an hour, or rather 26,000 kilometers per hour, you'll curve, but you'll be going so far horizontally that you'll miss the edge of the Earth and you'll just fall over and you'll keep missing it. In other words, you'll be in free fall, you'll be weightless, you'll be in orbit around the Earth. But it's only 50 miles an hour, so they're not going to get that. So we can use kinematics to work out actually what happens here. So the bus goes over a gap. It will fall under the influence of gravity. And in kinematics, we can separate out the motion of horizontal and vertical. Very powerful technique. So the idea is the bus will fall like this, right? We all intuitively get that. Now let's work out how bad does it get. So there's a 50-foot gap of 15 meters in real units, right? So in the movie, we can examine so we have, at that point, they're speeding up because there's a gap, so they want to clear the gaps, they have to go faster, but it's a straight horizontal floor, so we know it's not going to work. But anyways, they end up getting nearly 31 meters per second, 68 miles per hour. You can use another equation that we all love in Physics 101, which is that the distance traveled horizontally is equal to the initial speed times the time you're traveling, plus half times the acceleration times t squared. Horizontal, there's no acceleration. You've left the ground. Instead, all you've got is your initial velocity. The distance traveled is 15 meters. The speed you've done is 31 meters. And essentially, you clear the gap in half a second. Okay. Now, that's your horizontal motion, but what's happening to your vertical motion? Yeah, you are falling then. So how much do you fall? Well, same formula. Now it's the vertical height traveled is equal to the initial velocity times the time you've done. Initial velocity vertically is 0, right? You're on the road, right? You're not going up or down, you're on the road. Right? Going vertical. But there's definitely acceleration. The moment you leave that road, we begin the parabola. We know it begins to move down. And it moves down under the acceleration of gravity. Half times acceleration, which is g, 9.8 meters per second squared, times the time squared. The time it's been falling is half a second. So half a second squared, rearrange, and we find that it falls minus 1.2 meters. It falls 1.2 meters. So in other words, instead of clearing the gap, it would fall and smash the top of the bus, absolutely doing more devastation than the bomb it is underneath it, I suspect. So, terrible outcome. The only awkward thing is that the bus does do the jump, right? They don't CGI this. It literally does the jump. So how does it do this in reality? Well, they've got a ramp. They cheat. Well, they don't cheat. They do the real physics. They know exactly how steep a ramp to make, and they drive the bus so it gets kicked up a little bit vertically, and it just balances the amount it's going to fall, that initial velocity up, and it just hits the other side. And they film it in just such a way that you can't see the ramp. The thing that I can't understand is why they don't show you that. Why you just have an inclined road? Like, who cares? It's a bridge. It goes up at one, but like you could easily have just done the physics right instead of this weird scene. But anyways, so weirdly, this actually gets an M for modest because it actually does the physics in reality. It just weirdly lies about it in the film, and I don't know why they bother. Anyways, so a concept of fundamental import in physics, but in all science, is known as Newton's laws. We've discussed one of the first: a body in motion will remain in motion unless an external force is acted upon it. In other words, you will continue to move in a direction like you're free falling, unless you can somehow do an external force, like your little rockets fire out. That was the first bit in weightlessness. In the second, force equals mass times acceleration, or the change in momentum in the time taken. Good. We've done that already. The third and most important is that every force has an equal and opposite reaction force. Force applied, you get exactly the same force back in the opposite direction. You push something, it pushes against you. What film explores the force? Yes, I couldn't get the right cert. Unfortunately, Disney, brutal. But there is a scene that I love so much that I made this animation of it, in which there is an epic battle through the force between a little Yoda and a very big, much bigger Emperor Palpatine. And Yoda reaches out through the force, and force pushes Yoda. The Emperor Palpatine, and off he flies, right? Crashing into furniture at the other end of his very swanky palatial office. Now, I don't know how the force works, so I'm not going to investigate that. some midichlorians or some nonsense that was said. I mean, who cares? It's made up. Why make a reason for it? But just because I don't know how the force works doesn't mean that the force is unable to obey Newton's laws, and in particular, Newton's third law. So how should this scene have gone? This is really bad physics. So Yoda will push out through the force. I don't know what the force is, but it's a force, and there's an opposite and equal reaction force. That's the minus bit. Force action 1 on 2 is equal to the minus 2 on 1, right? The reverse. That's the mathematics of that third law. I push against something, and I can feel it pushing back on me. So there's Yoda in green. If he pushes Palpatine, then Palpatine in return will be pushing back on him. That's just inescapable. I don't know exactly what the force is, but it's connected, Yoda to Palpatine. So in response, there must be an equal opposite force back, Palpatine to Yoda. Now, the issue is Yoda's a lot smaller than Palpatine. So for the same amount of force applied, the smaller mass is going to go flying. So this is how the scene would go. So thanks to Newton's third law, we know that Yoda, far from being like heroic and stuff and just going, yeah, and pushing the much larger Emperor Palpatine flying, he actually, both would fly apart. And this is very much if you've ever been ice skating and you push against your partner, if you're both the same size, you'll both make a sort of equal kind of motion back. But if you're much heavier than your much lighter partner and you push them, right, they're going to absolutely fly. So how can this work? Because I do love Star Wars really very much. And I try to figure out, and I realized that Yoda's got like little clawy feet. Yeah. So if he holds, there's a little force applied from his foot on maybe that plush carpet, he can hold himself in place, and he's just got like just killer glutes, just absolutely rock solid, able to hold himself up. Then that's modest physics. All right, so anyways, I was really clutching at straws to make that scene work. In the interest of time, we're going to rattle through the next couple of key physics concepts because I want to get to your questions in the room and then online. So one of the fundamental, I would almost say laws, but yes, concepts in physics is that of the conservation of energy. Nothing is destroyed, nothing is created. It's just a rearrangement of the energy. A film that treats that quite disrespectfully, if I can phrase it that way, which is terrible for many reasons, is this one. It's just worth watching how bad it is. Okay, so yeah, it's terrible. I just keep watching it. It's really bad. In the film Armageddon, there is a meteor or a comet, some large object the size of Texas, I think famously they say. And it's coming in, it's going to be traveling at hundreds of thousands of kilometers per hour by this point. This is actually how the dinosaurs got wiped out. This is a real threat. So far, so good. We are actually monitoring the skies for exactly these kinds of objects. And NASA is now pretty sure it's tracked almost everything this size and above that might hit the Earth. So we're safe, at least from those sized objects. In the film, the concept is pretty straightforward. They send oil riggers to the surface to drill a hole right to the core to put Hollywood's favorite solution to everything, which is a nuke in the middle, set the explosion, and it splits the asteroid or meteor or comet, whatever it is in this instance, and it splits it in two halves, and the two halves go sailing by the Earth. And we're all saved by Bruce Willis's sacrifice. Sorry, spoilers. Spoilers if you didn't know, he dies. Absolutely garbage physics. There's so many things I could rip on this. It is such a unnecessarily bad film. Let's just focus on that last scene about the splitting of the we'll call it asteroid. for assuming a nomenclature on that. Now, this is where the conservation of energy comes in. Oh, so I removed the equation, which is lucky for everyone. So what happens, we know the energy of the explosion. We know that if assuming all of that energy was turned into the kinetic energy, the energy motion of the two halves, we can figure out how fast they move apart with this conservation of energy. You can plug in the numbers and you can see exactly how fast they move apart. You know how far away it is from the Earth, how long there is to this collision point, and you can actually work out just their separation. And instead, the iconic scene goes something like that. And I'm being generous if it's actually closer together. So basically, we don't survive. So in Armageddon, the energy required to split something the size of Texas and push it apart big enough to miss the target of 6,000 kilometers, which is roughly speaking out of the Earth in any one direction, is vastly, vastly larger than the nuke. This is why we don't try to send up nukes to explode asteroids, but rather try to nudge them ever so slightly. And if we can do it far enough in advance of their intersection with us, that tiny little bit of velocity over years means they'll just be moved out of the way. There's actually an even better way to do it by literally having a rocket just gently push against it rather than a nuke. It's more controlled. Anyways, either way, Armageddon, absolutely terrible. Now, it's not the worst. So one film that explores angular momentum, orders of magnitude issues, magnetic fields, EM radiation, and just general radiation, and confuses both conservation of energy, pressure, force, timescales, gravity, as well as plot and acting and logic, is the absolute worst film. Does anyone know what the film is I'm going to show? It is The Core. Yes. Here we go. Stop spinning. The core of the Earth has stopped spinning. So, okay. I mean, that would probably be bad, sure. I mean, the spinning core is what generates a protecting magnetic field, which prevents radiation from space hitting us. It stops the Earth's atmosphere from being eroded over the course of billions of years by the force of the sun's stellar wind, as well as the intensity of its light. The focused death ray thing, don't know where that came from, kind of crazy. But anyways, so I'll give them that. It's bad. It is bad news if the core stops spinning. So that's good, or like modest, right? Like not everything they show happening would happen at that point, but I would agree with them that it's bad. Okay, so far so good. They literally won't. That's just not true at all. So at this point of the film, it really just goes off the hinges. I can accept there's a plot conceit of let's get the emergency disaster thing happening. But what's actually going to happen? The microwaves, I mean, they're not affecting magnetic fields anyway. So the fact that that's stopped doesn't change anything. I don't know if you've seen sunlight, but it tends not to be a focused death ray. So why the microwave death ray? I don't know. Anyways, literally doesn't cook the planet, but we'll keep going. Okay. So what are we going to do about it? Oh, I love it. What if we could? No, we can't. That was absolutely true. If the core of the Earth has stopped spinning, you can't restart it. But okay, it's massive. It's the size of, they've literally said it themselves. It literally can't be done. But what if we could? Okay. Why is that good physics? Struggling to remember. Well, I guess it was good physics that one of them said you couldn't do it. Then the other said, well, if you could, and that's the bad physics. All right, let's see the next bit. Okay, Hillary's fine. Oh my God, not your finest hour. All right, so the solution, surprisingly to no one, is a nuke. The idea, very simple, is drill the nuke, drill down to the core. Don't worry about the fact that it's magma and it's all kind of weird stuff. Drill it and then place the nuke beside the core, set it off, and that's a big force, and that's going to start it spinning. Now, here's the main concept that my 4-year-old child understands. If they want to start a wheel spinning around, where do you push it? Do you push it like there to move it around, or do you push directly, really straight into the center of it? Which would you think is the better way to spin it? Probably the top bit, right? Like moving against the rotation to make it rotate around, not just push straight in. What's a nuke gonna do? Well, it basically is going to explode, and it's going to explode in every direction, left and right, up or down, all the same, roughly speaking, force. In other words, you're not going to get a net rotation. It's the equivalent of just pushing into the rim. So just even exploding nuke just literally doesn't work from that basic principle. However, if you study Physics 101 at Swinburne, which you will do if you do any science and engineering course with us, it's a mandatory core, and we do calculations like this, you can figure out just how much energy, assuming all of that force was applied to twist it around rather than just push straight in, as it will do, how much you need. There's an equation known as the torque equation. We're going to skip through the numbers, lots of great science. Hopefully you're all memorizing this to enjoy it later at home. Plug in some numbers, your favorite mass for the Earth and the radius. The inertial mass is enormous. Oh my God, how much, I've really spent too long on this. How much kinetic energy is required to get this thing spinning back up? How much does it need to spin? It's the day, that's the speed of rotation. Plug it in, and the number is being hidden, but is a difference of 10 to the 10. So 10 billion times the energy of the nuke, which is itself 1,000 times, I think, bigger than any bomb that's ever been used. So I thought Armageddon was bad from an energy perspective. The core is just so much worse. So physics is fun. You really get to go wild on some of these calculations. Now, but again, it's just on the basic principle of like, it just explodes and pushes into the core rather than turning it, right? It just doesn't work from that point of view. So this is literally the R-rated movie for this evening. Don't take my word for it. NASA thinks it's the second worst. The worst one, and I've never reviewed it because it's so bad, is 2012, and I just can't take it. Even for science, I can't make myself watch that film. In the last minute, before I go to questions, there is something I want to explore, which is science fact, not science fiction, and we think it's very good science indeed, and that is the search for dark matter. There is an invisible cloud of material that is traveling through us as we speak, billions of dark matter particles whizzing through your body without collision. It is a ghost. In fact, there's so much of it, it outweighs everything we can see in the universe 5 times over. Its gravity is responsible for holding us, our galaxy together. Iconic dark matter concepts, struggle to find many. Nibbler pulls it out. That's basically the one thing I could find as a dark matter reference. Not how dark matter is. It is not put out by a cute little creature, and it doesn't form little dense nuggets. In fact, that's the point. It's spread out. It is a ghost. It doesn't interact and clump together. However, we are building a detector that we hope will detect it. It is known as SABRE. It is built around sodium iodide crystals like this. We put 2 PMTs, very sensitive cameras, either end of it, and we wait for a dark matter particle to hit the crystal, cause a flash of light, see that flash of light, and then get the Nobel Prize that Brenton mentioned at the start. Now, this project is known as SABRE. It's led by Professor Elisabetta Barberio of UniMelb. The detector is encased in a 10-ton vessel that is in our Wantirna campus right now. Very soon, it will be driven to the bottom of an active gold mine in Stawell. This is one of the last photos I took of it being excavated, a 12-meter high cathedral-esque structure at the bottom, a kilometer underground in a gold mine here in Victoria. And now this is the version with it looking a little nicer. And then the final version will be when we seal it all up and it's airtight. and it's ultra clean. And there we will put the detector and we will start the search for dark matter, looking for that tiny flash of light as a ghost-like particle hits a crystal at the bottom of an active coal mine a kilometer under the ground. And if that doesn't convince you that science is better than science fiction, I don't know what will. Thank you very much for your attention. All right. Now, let's throw 2 questions in the audience. We have 2 roving mics. So who has a question? Question? Some hands, keep your hands up. And Brenton is on the case.
Hello, hi. Hi, Alan, huge fan of your work. I've got a couple of questions to ask. The first one is, did you do those animations yourself? Because they're very impressive.
No, I paid a guy lots and lots of money to do it, and I love them, but I'm also questioning just how much I've paid for those. But anyways, yes, yeah.
Second question is, you touched on a really important point at the beginning about how Hollywood is how a lot of people around the world get their information about science. And I think if the pandemic has taught us anything in the last few years, it's how frustrating it can be with like having so much misinformation about science out there. And I was wondering how you reconcile that as a scientist yourself. Do you feel frustrated when you watch movies and see misinformation, or are you able to suspend disbelief and just enjoy yourself?
Yeah. So look, I'm not like an absolute nutter. Like I don't scream in the cinema when I see bad science, but so people can go with me to films, right? Like it's not terrible for them as an experience. But yes, I do. I watch the film and I must suspend disbelief, and then I'll watch it again to be angry in my own time. But I think you hit the nail on the head. We've seen it in the pandemic. The issue, one of the dangers that perhaps isn't really recognized, but it's the failure to understand the scientific process, right? So most films will be solved by an outsider who's been neglected by mainstream science, and it's a really simple, singular solution that doesn't take years of concerted global effort to resolve a global threatening catastrophe of some kind, right? So like Armageddon, like the core. So that's really disappointing because obviously science is done in a considered fashion with large teams over many years of dedication, and often the implementation of the technological solutions require everyone to get on board for many, many years to resolve it. So that worries me, that we are conditioned to believe in quick, singular solutions to global problems. And the reality, of course, is global problems take very long times and very large amounts of effort to change. And I think that's actually the danger of the Hollywood version of science that we see. And I think the pandemic showed that up horribly. Thank you. Yep.
Following up on that, do you think there should be a rule in science fiction movies that says that if it's the correct theory at the time, we should adhere to it? Like dinosaurs and humans don't coexist in movies or something.
Oh, yeah, right. Okay. Yeah, this is a difficult one, right? So there's the, because it is at the end of the day a creative process, right? So where do I stand on this? I don't want to be, a killjoy where it's, you can't have, a version of the world where dinosaurs and humans coexisted and there's kind of a fun interaction, because my kid loves Ice Age, right? And she'd be devastated if she couldn't watch Ice Age anymore. But it is a real problem because there's many people that incorrectly think that dinosaurs and humans coexisted, right? So as a result, in part of films. So I don't know what the solution is, except more education, right? Better efforts. But then again, recognizing the fact that people still have these misconceptions even so. I guess the danger, so I guess from as a personal point of reference, my own thoughts on this, it's fine to set a world where there's one thing or whatever the scenario is that you as the narrator want to explore, the creator, and then you are self-consistent with your own rules, right? I guess that's how I see science fiction. So I'm like a super nerd on that, which is why, Yixing Qing instead of Star Trek, like there's a Dark Forest trilogy instead of Star Trek. But yeah, the point around people's misconceptions about our own history is really worrying. And I don't know how you easily solve that. And I would say that perhaps the challenge is not necessarily the movies in that particular instance, but perhaps some bad actors who are intentionally misconstruing the evidence and set up museums that literally show dinosaurs and humans coexisting, which is a bit different from Ice Age. Yeah, so I think, yes, we'll, so we're not going to solve all the problems of the world tonight, but I do want to recognize that we can do better science and still get great films. Yep, at the back.
Might just go to one from
was there a
online. What physics movie rating would
Oh,
you give Don't Look Up?
very good. Thank you, anonymous attendee. So I only recently watched this because I couldn't face it during the pandemic. Like I was just too fragile to watch. And I watched it and that's where I did scream. Like I was sitting at home just going, oh my God. And I was doing that because I was the scientist and the frustration, like listen to the evidence, the data's here. I was the science communicator on TV going, why aren't you listening to this? And then I was also kind of just the general public going, it seems too big to address. The forces arrayed against us. So yeah, I'm glad I waited until after the pandemic. So the science was really good. There's actually the scene that I really greatly enjoyed was the discovery scene. They were actually in a telescope that we use here in Swinburne. I think it's I think from memory it's a VLT. I could be wrong on that. But anyways, and I can tell you, you don't have the lights on inside the observatory when you're using the giant telescope to look at very faint stars. You're going to blind it. But apart from that, the scene where they're looking at the little smudge of light and they're tracing it out, and it's kind of how you would do it. I mean, there's an automated process where you wouldn't be doing it by hand, but still, it's a nice moment. So I actually think the science wasn't terrible, and I think the messaging was a little blunt, but I think was pretty correct, depressingly in some instances. So yeah, I actually rate it very highly. Yep.
Cool. So this whole presentation is pretty much, we're talking about education within an entertainment medium.
Yes.
I'd love to know your opinion about entertainment in an education medium. So for example, one of the reasons why I'm studying physics now is because my year 12 physics teacher, instead of it being like, oh, you throw a ball, work out how far it goes if it's at this velocity, for example, he'd flavor everything and say it's a zombie apocalypse, you're throwing a Molotov cocktail.
Yeah, okay.
What force do you have to do in order to hit that zombie and save everybody?
Yeah.
What is your perspective on when you incorporate entertainment to that sort of fantasy level into, I guess, a classroom space while still be able to have accurate science?
Yeah, wonderful question. Yeah, and that was great teacher that you had to do that. Look, I think context matters. It matters that when I talk about the rotation, rotation force calculation that I showed about the space station, we're talking about a space station rather than a merry-go-round, because who cares about merry-go-rounds? Or a slowly spinning galaxy, like Vera Rubin did back in the 60s, to then show that there was extra gravity unaccounted for, which implied dark matter. So I think the context matters, and you can still be accurate and faithful to the physics or to the science and have these cool scenarios. And in fact, there's a really great film known as Interstellar, and the bookcase, well, okay, apart from the last bit, but almost everything else is perfectly accurate. And it's because Kip Thorne would get, the science advisor Nobel laureate, would get phone calls from Chris Nolan, like in the middle of the night, shouting at Kip, going, I need this scene to last longer. You've got to get the gravity to make it last longer, or whatever. Right? So he worked out ways to have the time dilation be as long as it needed to be for the plot. But he gave enough clues in the physics, so there's a tidal wave thing, that his students could work out the mass of the black hole that was doing the time dilation from that, as well as the rocket. So in other words, he was giving all of these physical clues for his own students to then, which he set them to then solve. And I think that's a profoundly interesting way to solve those equations. So look, I think if we can make the context more entertaining, then why not? It's often the case that it's the real world when you actually get to university as distinct from high school. That's when it really becomes fun, or at least did for me, because I was exploring the real crazy complex world with physics. It wasn't these idealized situations anymore. There was real context, and it mattered what the numbers were, or the equations were applied. So for me, university is when science became a lot more real and fun, because the context matters. But I also like the zombie one too. I think it's pretty cool. One more question, yeah, and then oh my goodness, yeah.
Just following up on the previous question again.
Yep.
So do you think we should, as we are criticizing movies based on the science rating, we should also criticize professors and teachers for making science boring?
Do I think that we should have anonymous rating of professors in their teaching? What do you reckon, Brenton? I don't think so. No, look, this is, so we do get rated actually. I don't think there's a box that's where is it entertaining or not, but we certainly do get feedback from students in our lectures, which you take very seriously. I can assure you, every semester we review them. And I can't help but imagine that if you make a lecture really dry and boring and uninspiring and unengaging, you're probably going to get a response that's not great from the students in their feedback. I don't know that we should have a box necessarily for how fun was it, but yes, there's people are going to switch off. It's boring. So but it's physics. You could like physics is genuinely fun. It's the description of everything. So how can you make that boring? I don't know. Did you want one final question? You got a cool time?
I think I've got a cool time.
Oh, okay. All right. Well, look, thank you all so much. And I'll throw back to Brenton.
So I'm just going to say thank you all for coming out this evening. Thank everyone online who has joined us. And I hope that you do get to another activity during this week, National Science Week. There's a lot on, and certainly feel free to come down and talk to us as well afterwards. So good evening and take care.